Welcome back, everyone. Thanks for watching. In this video, we're going to talk about different tests that you can apply to an infinite series to determine whether it will converge or diverge. So first, I'll give you a summary of what the tests are. I hope you're familiar with them at this point. So now you can do some examples to see which test is applicable for a particular series. So let's get to the summary of the test, and then we will take a look at some examples. So if you have a series, an infinite series, an, you want to know, will it converge or diverge? Well, you apply some tests. So the first test that I will always recommend you to test is the nth term divergent test. So you pretty much do the following. So this is the nth term divergence test. So this will test for divergence, not convergence. So keep that in mind. For this test, you take the limit as n gets larger of your sequence an, and you see what this limit is. If this limit is non-zero, so it could be infinity, negative infinity, does not exist. If it's not zero, then we can say that our series is going to diverge. If the limit is zero, then the test is inconclusive. It doesn't help us to determine whether it's going to converge or not. So we don't really know. So if the limit is non-zero, then of course you can say it diverges. That's the first test. You always want to apply. The second, so the rest really depends what kind of formula you have for your an. But I'm going to try to go in order. The next thing I'll look for is it a geometric series? So is it a geometric series? So geometric series are series of a very specific form. So you have two forms for the geometric series. Your n can start from 0 to infinity. Then your formula will be 8 times r to the n. That's one version of geometric series. Another version will be the sum starting from 1 to infinity of 8 times r to the n minus 1. Now, both of these will converge for the following cases of r. So if r in absolute value is less than 1, then your series is going to converge. And it's going to converge to this value, a over 1 minus r. However, if r in absolute value is greater or equal to 1, then you know that series will diverge. So these are the two conditions we know for a geometric series. Now, if the series is not a geometric series, then you try to say, okay, what does it look like? Could it be a p-series? So p-series is another type I always look for when it comes to testing will it converge or diverge. These are the p-series. P-series will have the form n starting from 1 to infinity of 1 over n to the power p. So p is a power. Now, this again, we break it down into two cases. We can say that this will converge if p is greater than 1, and it's going to diverge if p is less than or equal to 1. So these are the two cases for the p-series type. Another type you look for, very specific, is the telescoping series. So telescoping series are, they're very rare. Sometimes you try to write out the terms and see if they cancel each other out, so you get a formula for the nth partial sum. So usually one way to recognize it is if you can use the partial fraction decomposition to write out your an formula, and then when you write out some terms, some of the terms will cancel. You'll be left with either one of the term, which is the nth term. We're going to take the limit of that nth partial sum, and if that limit goes to a finite value, then of course the series will converge. So that's one way to approach telescoping series. So often you use partial fractions to express your formula for an. and then terms will cancel out. And then you also get a formula for the nth partial sum. So let's call that Sn. So the nth partial sum, we're going to call it Sn. So when you take the limit of this nth partial sum, if this goes to a finite value, then you know your series is going to converge. If it diverges, then of course, it's going to diverge. So that's how you can work with the telescoping series. All right, so we got to the type. So we have geometric, p-series, telescoping series. The next test, so if it's not any of these type, then you can apply this test. So this is our number 4. We can see if we can apply the integral test. So integral test, in order for you to apply it, you have to make sure 3 conditions are satisfied. So you have to verify that, so you have some an, you call that a function of n. And you want to make sure that your function satisfies the following conditions. You want to verify that it is continuous on that interval, positive, meaning your values are always positive, non-negative. Even if few are negatives, you can throw them out. And also you want to make sure it's a decreasing function. So I usually abbreviate this using CPD. So once you verify that, then you can use the integral test. So for instance, you will do the following. You will take the integral of, let's say, from 1 to infinity. Let's go with that. Of this function, f of n dn. If this converges, if this improper integral converges, then your series will converge. And if this improper integral diverges, then of course the series will diverge. So these are the conditions for the integral test, which we'll discuss in the example. So I hope you're familiar with them at this point. Next thing you want to do is some sort of comparison test. Now, if you're unable to integrate that function, or it's difficult to integrate, you can try to do comparison test. Or if that's also difficult, you can try the limit comparison test. So I'm just going to summarize them, not in so much detail. So if you have, let's say, positive terms, so 0 less than or equal to some an less than or equal to bn. If that's your sum, so if you're looking at their sums, we can say that if, let's say, if the series an, which is less than the series of bn, if this diverges, then the one that lies above the sum bn diverges as well. Now, if you switch the order, let's say the second condition, if now the sum bn, which lies above an, if that converges, if this converges, then whatever lies below will converge. So then the series an converges as well. So that's how you apply the comparison test. For the limit comparison, well, you construct a sequence bn, and then you do the sum. So you create a sum bn, and then you take the ratio. So you do the limit as n goes to infinity of your an over bn. If this is a value L, which is greater than 0, it's a positive real number, then both series, both bn and an will diverge together or converge together. So they will both diverge or converge together. So that's how you apply the limit comparison test. Then the last test I'm going to mention is the ratio test. So this is number 6, the ratio tests and root tests. So for ratio test, you're comparing ratios of the following terms. So suppose you're given the series an. So you're going to do the following. You're going to take the limit as n goes to infinity in absolute value of an plus 1. So one term after an, you divide that by an, the previous term. And if this limit is L, now we're going to break it down into 2 cases, 3 cases really. So if L, this L is greater than 1. If the L is greater than 1, then the series diverges. Second case, if this L is less than 1, then the series converges. Not just converges, it actually converges absolutely. So because you put the absolute value around your terms, it's going to be an absolute convergent. So keep that in mind. And the third case, if L is exactly 1, then the test fails, so inconclusive. So you'll have to go to another test. Similar condition for the root test. So again, if you're given a series an, then for the root test, you do the following. So you take the limit as n goes to infinity of the nth root of an absolute value of an. So when you have powers, you often want to use the root test. And if this is equal to some L, then we fill out the same conditions as this one. If L is greater than 1, it's going to diverge. If L is less than 1, the series converges absolutely. And if L is 1, inconclusive. So similar conditions as the ratio test. I'm going to skip the alternative series test. That will be for another video. So let's take a look at these 6 tests and see how you feel with examples. Okay, so here's our first example. We want to know if this series will converge or diverge. All right, so it's not a geometric series, right? Because it doesn't have that form we mentioned above. It doesn't look like P series either. It's probably not telescoping either. I feel like I want to do the integral test. So the reason I want to do that, because I see a ln here and I see 1 over n. If I use some sort of u substitution in the integration, I think I can work this one out nicely. So, but I need to check for 3 things, CPD, right? So for this one, we're going to do the integral test. So we're going to say, okay, let our function f of x stand for 1 over x times ln of x squared. I'm going to choose that to be my function, just writing our an as a function of x instead of sequence. So, well, I want to make sure 3 things, C, P, D. Is it continuous? Is it continuous on the interval 2 to infinity? Well, yeah, there's no problem in here. I can plug in any real value between 2 to infinity. Nothing makes it undefined. So continuous is checked. Are the outcomes always positive? Yeah, when you plug in any value from 1 to infinity, this will always be a positive number. So positive terms, so that's also checked. Now, is it decreasing? So for decreasing, you can do that in 2 different ways. You can show that your an term is greater than or equal to the next terms, or an plus 1 is less than or equal to an. Or you can show that the derivative of this function is always less than 0. Now, I claim to you that when you take the derivative of this using quotient rule, it is going to be negative. So I don't want to do that. I think you can handle that at this point. Since we're up to series, integration, differentiation should be very quick for you. So this is a decreasing function on this interval, so checked. All right, so my CPD criteria are satisfied. Now let me go ahead and do the integration. So I'm gonna say, let the integral from 2 to infinity of 1 over x times ln of x squared dx. But what is this equal to? You treat it as an improper integral. This is the limit as n approaches infinity of the integral. Actually, let me not use n so we don't get confused. Let's use b, some b. So we have 2 to b of 1 over x ln of x squared dx. So let's go with some u substitution. So we're going to let u to be ln of x. So you know du is 1 over x dx. And that's exactly what I have in my integrand. So then my integral becomes the limit as n and b goes to infinity of the integral. So I'm going to ignore the limit of integration for now since I'm switching variables. This is 1 over u squared du. And then u squared, you can bring it on top to make it a u to the negative 2. So you can use power rule of integration. So this is equal to the limit as b approaches infinity of u to the negative 1 over negative 1, going from the limit of integration, but I want to plug in what u is so that I can bring in my limit of integration. So I have the limit as b approaches infinity of negative 1 over u. Well, that's ln of x. Now I can bring in my limit of integration from 2 to b. So all this time I ignore my limit of integration because I was work with the u variable. My limit of integration belongs to x. All right, now I'm ready to evaluate this limit. So this is the limit as b approaches infinity. Plug in the upper limit of integration minus 1 over ln of b plus 1 over ln of 2. Well, ln of 2 is just a number, so that wouldn't bother us with the limit. So what is this limit? So as b goes to infinity, this will be 0. So we have 0 plus 1 over ln of b, finite value. So what does that mean? Well, that means that since the integral converges by the integral test, this series will converge. So we can say that by the integral test, our series, which was the sum from n equals 2 to infinity of 1 over n times ln of n squared, converges. So we justify that by using the integral test. All right, let's take a look at this series. So we're going to go ahead and apply the nth term divergence test. So we take the limit as n approaches infinity of cosine of 1 over n. So if you take the limit of this, we can write it as cosine of the limit as n approaches infinity of 1 over n. Well, we know this limit is going to be 0. So this is cosine of 0, which evaluates to 1. Now, since this is not equal to 0, we know by the nth term divergence test, this series diverges. So by the nth term divergence test, the series from n equals 0 to infinity of cosine of 1 over n diverges. So for this particular example, I want to use the ratio test. The reason I want to do that because if you try the nth term divergence test, it's going to fail. Integral test, I don't want to do it because we don't really know how to integrate factorial. So the best way to go by, one of the best way would be to actually apply the ratio test. Since I see a factorial, I always want to do ratio test. So let's apply ratio test here. So this is your an term. That means an plus 1 term would be to substitute n plus 1 where there is n in the formula. So it'll be n plus 1 over n plus 1 factorial. So I substitute n plus 1 here and here. So this simplifies to n plus 2 over n plus 1 factorial. So let's do the ratio test. So the limit as n goes to infinity of a sub n plus 1 over a sub n, we're going to take the limit absolute value of their ratios. So this will be the limit as n goes to infinity of, so a sub n plus 1 is n plus 2 over n plus 1 factorial divided by a sub n, so that's our original formula, n plus 1 over n factorial. All right, now a little bit of algebra and then we're pretty much done. Keep, change, flip. So I'm going to take the limit as n goes to infinity. Now we should also drop the absolute value since all of these terms are going to be positive as n gets larger. So I'm going to drop them. So I have n plus 2 over n plus 1 factorial times, I reciprocate the bottom fractions, n factorial over n plus 1. Now let's do a little bit of simplification. So I'm going to go ahead and rewrite this term. So we know that n plus 1 factorial can be written as n plus 1 times, so you subtract 1 from it to get to the next value. This will be n, and then n minus 1, all of them. I'm going to stop at n factorial since I have n factorial in the numerator. So this is equal to the limit as n goes to infinity of n plus 2 times n factorial over n plus 1 factorial. I'm going to rewrite this way. So by definition of factorial, that's n plus 1 times n factorial times n plus 1 from before. And now we can cancel out the factorials. So this and this will cancel out. So we have the limit as n approaches infinity of n plus 2 over n plus 1 times n plus 1. Now, if you take the limit of this thing, we know the denominator has degree n squared, degree 2, and the numerator is 1, so the bottom is going to grow faster than the top will be 0, which is less than 1. So by the ratio test, this series converges, absolutely. If your limit is less than 1, it's a convergent, absolutely. So by the ratio test, our series from n equals 1 to infinity of n plus 1 over n factorial converges, but we also know it converges absolutely. For this particular example, well, I see that I have powers of n, and this is a 2, 3 to a power. I think I want to rewrite it. It looks some sort of a geometric series. So let's go ahead and rewrite by using laws of exponents. So you have the sum from 0 to infinity of, so 2 to the 2n plus 1, you can write it as 2 to the 2n by laws of exponents times 2, because that's 2 to the 1 power. And on the denominator, that's just 3 to the n. Now, this one right here, 2 to the 2n, that can be written this way. So you can write it as n equals 0 to infinity of the sum. 2 to the 2, that's 4 to the n times 2 over 3 to the n. So I just rewrote 2 to the 2 as a 4. That's raised to a n power. Now, since these two have n powers, I can put them together, write it like this. So you have the sum from n equals 0 to infinity. So bring the 2 on the front. So you have 4 over 3 to the n power. Now, this is a geometric series and starts at 0 and goes to infinity. So you can identify that this is your R and this is your A, since we have the exact format we wanted. So by the definition of a geometric series convergence, this R is 4 over 3, which is greater than 1. So what do we say? It's going to diverge. So because R is greater than 1, this series diverges. So what can we say about the original series? Well, diverges. So we pretty much wrote the original series as a geometric series, and we identify R is 4 over 3, which is greater than 1. So it's a divergent geometric series. So this sum, which was given to us from 0 to infinity of 2 to the 2n plus 1 over 3 to the n, this is a divergent geometric series. Here's another exciting series to work with. So if you try the nth term divergent test, it gives you 0, so it doesn't work. It fails. So we're going to come up with another test. It doesn't look like geometric. It doesn't look like P series yet. It looks like I can do some sort of comparison. So check this out. So we know that if you try to use this comparison, let's say n over n squared plus 4 with n over n squared. So since this has more on the denominators, they have same numerators. So we can ignore that, compare the denominators, since the left side is greater than the right side, so the overall fraction value is less. So this is a less than or equal to. So that's the comparison I came up with. Now 1 over n squared, well, that's simply 1 over n. So now if you look at the series from 1 to infinity of these, the inequality still holds. So I'm going to look at this series right here. Now, what do we know about this series? Well, this one, that's a P series where P is 1. This diverges. So this is a divergent P series. So since it is divergent, the comparison test doesn't help us because we want something, whatever you find greater, if it converges, then whatever lies below will converge. So that doesn't help. So that's why I'm going to go with the limit comparison. If the limit comparison gives me a value, finite value greater than 0, then the original series will also diverge because they behave the same. So we're going to apply the limit comparison test. So let's do limit comparison test. So this is your an, that's the original formula, and the one you came up with, this will be the bn. So we take the limit as n goes to infinity of an over bn. So this would be the limit as n goes to infinity of an, which is n over n squared plus 4, divided by bn, that's 1 over n. And simplifying this algebraically, we will have the limit as n goes to infinity of, so n over n squared plus 4 divided by 1 over n, same thing as multiplying by the reciprocal of the bottom fraction. So you will have n squared over n squared plus 4. In this limit, we know that this is 1. Since they have same degree top and bottom, the limit as n goes to infinity, it's their leading coefficients, the ratio of that. Since this is 1 greater than 0, we say that by limit comparison, this series will behave just like the one we compare it with. Since the one we compare it with diverges, this will also diverge. They behave the same. So by the limit comparison test, the series that we're looking at from 1 to infinity of n over n squared plus 4 diverges. And you can also write a little bit more statement, since we're comparing it with this series, which is sum from 1 to infinity of 1 over n diverges. That's your bn. But by the limit comparison, this is true. Let's take a look at this series. So we're looking at negative 1 to the n power times n over 2 to the n power. So again, if you see powers, go with the ratio test or the root test. I think this is easy to work with by the ratio test. So I'm going to go with the ratio test. So another example of ratio test. So this is the formula for your an terms. So that means an plus 1 would be plugging in n plus 1 everywhere there is n. So you have negative 1 to the power n plus 1 times n plus 1 over 2 to the power n plus 1. So that's the a sub n plus 1 term. So the ratio test says to take the limit as n goes to infinity, absolute value of an plus 1 over an. Take their ratio. So I plug these in. So I have the limit as n goes to infinity of an plus 1 term. So that's negative 1 to the n plus 1 times n plus 1 over 2 to the n plus 1. Now dividing it by a sub n, same thing as multiplying by its reciprocal. So multiply by the reciprocal of it, 2 to the n times -1 to the power n times n. So instead of dividing by an, I multiply by its reciprocal. So algebraically, that's true. Now let's simplify. Now, if you were to take absolute value all of these terms, the absolute value will make these disappear. So these negative terms will drop off. So you're left with the rest. So let's simplify that and drop the absolute value. So we take the limit as n goes to infinity of n plus 1 times 2 to the n over. Now this right here, 2 to the n plus 1, I can write it as 2 to the n times 2 to the 1, because that's by laws of exponents is true. And we still have an n from the next fraction. All right, so let's go ahead and see what this limit is. Now before that, I'm going to simplify a little bit more. I see I can cancel out 2 to the n, 2 to the n. And now I can simplify, write the limit as n approaches infinity of n plus 1 over 2 times n, so 2n. Now, if you take this limit, again, the degrees of the numerator and the denominator are equal, so it's their leading coefficients, which is 1 over 2. That's less than 1. So by the ratio test, this series converges absolutely if it's less than 1. So therefore, we can say that the series that we're looking at, n equals 0 to infinity of that an, so n equals 0 to infinity of -1 to the n times n over 2 to the n, converges absolutely by the ratio test. All right, so another example of ratio test. All right, so we want to determine if this series will converge or diverge. So I see a cosine, I see n squared plus 1. It looks like we want to do some sort of comparison test here. So I can set up my comparison this way. So I have cosine of n pi over n squared plus 1. And then I'll take the absolute value of this. So we have absolute value of cosine of n pi over n squared plus 1. So the cosine, if you take the absolute value, the oscillation from -1 to 1 becomes just 1. So you take the absolute value of the negative values. So we can simply say that the value I can put on the numerator for the second fraction is 1, if you take the absolute value of cosine. So then this would be less than or equal to that, because you have cosine n pi on the left side. So now I know this is going to be less than or equal to 1 over n squared, because again, this will be a little bit less than 1 over n squared because of the plus 1. You're making the denominator larger. And if you look at their series, so if you throw in the sum in the inequality, and from 0 to infinity, same thing from n from 0 to infinity of this sum, and from 0 to infinity. Now this is a p series, but this starts from 1, n equals 1, to infinity of 1 over n squared, and we know that converges. So before I make my claim, I'm going to do the following. Write out the first term when n equals 0. So if I write out the first term, so you have the sum starting from 1. So write out the first term when n equals 0. You'll have cosine of 0 pi over 0 squared plus 1, plus the next terms, I'm just going to keep it in this condensed form, n equals 1 to infinity of cosine of n pi over n squared plus 1. And now I can do the comparison test here, because I wrote out the first term, because the first term, this is the term when n is equal to 0. And this is actually just 1 over 1, because cosine of 0 is 0. So this term is just 1, finite. So we just need to know if this will converge or diverge. If it converges plus 1, it's going to converge. If it diverges plus 1, it will still diverge. So it wouldn't really make a big difference. So that first term wouldn't really make a big difference in our convergence or divergence test. So now this series, let's take a look at from n equals 1 So we're looking at from n equals 1 to infinity of cosine of n pi over n squared plus 1. Same thing for the second one, and same thing for this one. And now we can make our claim. So this is a convergent p-series. So therefore, because it's above the one we're comparing it with, it will also converge. So by comparison test, the series we're looking at from n equals 1 to infinity of cosine of n pi over n squared plus 1 converges. So we can write 1 plus that, since this was one of the term. Even if you didn't write it, that's actually fine. But just to be super safe, we want to mention that as well. This will converge by the comparison test. All right, here's another interesting one. So we have the sum from n equals 1 to infinity of n over 3n plus 1 to the n power. So for this one, I'm actually going to go with the root test because I see a power of n. I want to go with the root test. It's actually more convenient. There's actually another way to do it now that I'm thinking about it. You can do the root test. You can also do the geometric series test. So I'll show you in both ways because this is it seems like I can write it in the geometric series form as well. So let's do it. Let's do the root test first. So let's do this one first. So if I take the limit as n goes to infinity of the nth root of absolute value of that formula, n over 3n plus 1 to the n power. So since we're taking the absolute value, all the terms inside the absolute value are positive, so I can cancel out the nth root with n, the power. So you'll have the limit as n goes to infinity of 3n over, so these guys cancel out. So you'll have n over 3n plus 1. And then when you take the limit of this will be, again, the degrees are same, so it'll be their leading coefficients, 1 over 3, which is less than 1. Great. So what does that mean? This means by the root test, this converges absolutely. So by the root test, our series n equals 1 to infinity of n over 3n plus 1 to the n power converges absolutely. Absolutely, because we took the absolute value of it and it converges. That's what we call it, absolute convergent. Now let me show you the geometric series way to approach this problem. So we're going to rewrite them. So divide all of these terms by n. So you'll have the following. So here's the geo series test. So we want to see if this is a geometric series. So if I divide every term by n, so n starts from 1 to infinity of, you'll have, so n divided by n, that will be 1 on the numerator. 3n divided by n, that will be 3 plus 1 divided by n, so that will be 1 over n to the n power. Well, now we can do some comparison. So this series is definitely less than or equal to this series, sum from 1 to infinity of 1 over 3 to the n. Because as n gets larger, this is a positive term, 1 over n. So I'm comparing it with 1 over 3 to the n power. So that means that, well, this is a geometric series. This is a geometric series with r equals 1/3, which is definitely less than 1. So 1/3 is less than 1, so therefore converges. So this will converge. Now, if you want to talk about absolute convergence, you'll have to take the absolute value of your terms and then talk about absolute convergence, which we got by doing the ratio, the root test. We got an absolute convergence. So some series you can do more than one test. Again, you decide what's convenient, what's easier for you to work with. All right, so here's our last example for today. So I have this series and I want to see if it converges or diverge. Now, since it has two different terms for one formula, I'm going to write out the terms, and I think it's a telescoping series. So let's go with that. So write out a few terms. So this series, if you let n equals 1, you will have ln of 1 plus 1, that's 2, in square root. So I forgot to put the square root. Minus ln of 1 square root of 1. And then, so this is n equals 1, plus the next term n equals 2. So for n equals 2, you'll have n equals 2. So ln of square root of 3 minus ln of square root of 2. And then for n equals 3, you will have ln of a square root of 3 plus 1, that's 4, minus ln of 3. And just keep on going. So you see where this is going. So I see that some of the terms will cancel. So going with telescoping series idea is good. So progress so far. So so write down a few more terms up to the nth term. So so the nth term, so I'm going to write a few more terms, but before I want to write the nth term. So here's the nth term. The nth term will just be the formula. So you'll have ln of a square root of n plus 1 minus ln of n. That's the nth term. Now let's go ahead and write down the term before the nth term. So I'm going to go ahead and write down n minus 1 term, the one that's before n minus 1, before n. So so you see the formula, you do n minus 1 here. So you'll have plus ln of n minus 1. So that will just be n in square root minus ln of n minus 1. So that would be square root of n minus 1. So now let's go ahead and write out the n minus 2 term. So that's this one right here. This will be n minus 2 term. So if I sub in n minus 2 in here, I'll have ln of square root of n minus 2 plus 1. So that's n minus 1 minus ln of n minus 2. So that's n minus 2. All right, so that's the n minus 2 term. All right, now we can have a better idea where this is going. We can start canceling terms. Well, I know this is going to be 0. ln of 1 is 0, so that disappears. So ln of square root of 2, negative ln of square root of 2, that cancels. Ln of square root of 3, negative ln of square root of 3, that cancels. And you can see that this guy right here, it will also cancel with something here. So every other term seems to cancel plus minus of the same term. Now, if you go to the bottom ones, nth term and then n minus 1 and n minus 2 terms, it looks like this one and this one cancels. And then this one and this one cancels. So I bet if you write out n minus 2 term, this will also cancel. But there's nothing that will cancel this guy right here. So that's your partial sum. So your formula for this one survives. Everything canceled except for that term. So your partial sum, Sn, is going to be this formula, ln of square root of n plus 1. Now let's take the limit of this. If this converges, the series will converge. If this diverges, then the series will diverge. So take the limit as n goes to infinity of your partial sum. This is the limit as n goes to infinity of ln of a square root of n plus 1. And as n grows, ln will also grow. So this is actually infinity. So that means that our series actually diverges. So this means that this is a divergent telescoping series. So that's the conclusion we can make for this particular series. All right, so I hope this helped you understand series a little better. Again, try more examples, see how you feel, see which test is applicable. I did a very useful test. There's also another test, alternative series test, which I didn't mention in this video. That's another way you can determine if a series converges or diverges. That'll be for next time. All right, I hope you enjoyed. Have a lovely day. Take care.